Hi, this is Paul again, and I've got another new video, and I'm calling this Quad Step Phyllotaxis 3D Order Lesson 4. In my last video, Lesson 3, I showed that the cube and octahedron can go a four-fold Quad Step Phyllotaxis system. And as you can see in front, I can make 8 arc segments with a 32 ball array of Phyllotaxis. But this 832 system is only based around one cube and one octahedron. Now I'm going to hide everything and just show the octahedron. And now I'm going to reorientate it to the vertical axis position. And now I'm going to give it a ring, and it will be the same diameter as a spherical dodeca and the same for the octahedron. Okay, and now I'm going to hide the solid octahedron and just show the vectors. Now we've got 6 vectors altogether, so I'm giving you a better view. Now you can see that the 6 vectors of the octahedron pass through the midpoints of the edges of the dodeca, and they carry on to the circumference of the spherical size. Okay, there are 30 edges to the dodeca, so that is going to give us 30 vectors. Let's take a look. Okay, I'll bring this vector arrangement to the vertical axis again. Okay, while we're on the subject of these 30 octahedron vectors, I'm going to show you the vector arrangement for the 5 colored cubes. This stuff is from my earlier videos I made a few years back. I showed that the 5 colored cubes could give us a color-coded 10-20 vector system for the dodeca. Okay, now I'm going to add to the 20 vectors of the cubes the 30 vectors of the octahedron, the yellow vectors. Okay, now I'm going to hide the 20 color-coded vectors of the dodeca coming from the cubes. And now I'm going to change them yellow vector colors of the octahedron, and they're going to match the colors of the cube. And now I'm going to give it a little spin around, and you can see that the colors of the octahedron match the color faces of the cubes. Maybe the use of these vector colors is a means to identify the geometry of vectors of diseases in the future. But with only a few people taking an interest in this order, I guess we're going to have to wait for chaos to be thrown out the window. Anyways, I think we'll return to where I left off. I'm showing them 20 yellow vectors again. So what I've done with them vectors, I've joined all the ends up to make a polyhedra. Now I'm going to give it a spin around, and you can see how the polyhedra goes together. So now you can see it's formed an ICOSIDODECAHEDRON. I'm going to call it an ICOSIDODECA. There's no need to go so highfalutin. Okay, I'm going to change that outline into a solid ICOSIDODECA, and it looks pretty nice with the colors. Well, I think so. Now notice as this is spinning around, you can see the edges of the red dodecahedron. Now what's important also is that the vertices of the dodeca and the Icosi both have the same spherical diameter. Okay, now I'm going to focus on the octahedron and the Icosi. Now first I'm going to show the octahedron in the dodeca, and notice how them edges are 90 degrees about. Now I'm going to hide the dodeca and bring in the ICOSIDODECA and show the outline. What you are looking at is one octahedron in this Icosi outline, but there are actually 5 of these octahedrons. Okay, now I'm going to give you an array of 32 balls. That will be 8 sets of 4 colors. I'm going to show you the ICOSIDODECA colors also for a glimpse. And then I'm going to show you a little animation, giving it 4 segments. Now what I'm showing here is something very important. It means that all the vectors of the ICOSIDODECA are fourfold. And you can see I'm giving you a 4, 8 and 32 fold array. Now by using these vectors of the ICOSIDODECA, it can also affect the geometry of a dodeca also. Let's go back to them 8 arc segments again. Now we'll fade into the dodeca. And now we'll give this assembly a little spin around, and you can see how the geometry goes. Now you can see the 8 arc segments aligning perfectly to the vertices and midpoint geometry of the dodeca. Isn't that something? Now this wonderful symmetry is shown in 3D reality. It's not a theory. Okay, now I'm going to take you to the 5-fold geometry. Now this 5-fold geometry is based around the vectors of the Icosa this time. Now I'll show the colors for the ICOSIDODECA. Now I'm going to add a group of 4 colored balls, just like I show. And we can hide the white balls. Now I'm going to give them balls a 10 copy array. And now we're going to show the arcs as 10 segments. Now the arcs can go to 40 segments also. But I'm going to take it back to the 8 segment. And we're going to rotate this around for a look. So now you can see in front of you that we have quad step Phyllotaxis. Now in front of you, you can see 4 latitude rings, and we have a polar array of 40 4-colored balls. Now these colored balls can be arranged in 10 segments, so this is basically a 5-fold system. Okay, the next job is to show you the 3-fold or 6-fold or 12-fold system. So the 6-fold system is based around the vectors of the dodeca. There are 10, 20 vectors in the dodeca. I'm just showing the center ring at the moment. It can probably be made into latitude rings also. I haven't got that far yet. Okay, I think I'll show this animation in the top view also. Because in the top view you can really see the 12 segments better. And you can also see the little pyramid in the center, which is the vertex of the dodeca. So basically it's not that complicated. The 5-fold are based around the vectors of the Icosa. 4-fold comes from the vectors of the ICOSIDODECA, and the 6-fold comes from the vectors of the dodeca. So I guess that's all for today. So to the few people that don't like chaos, this is Paul saying thank you very much for watching my video.